and that's why I have to finish it by today. So in this lecture, I will try to finish this lecture on gameplay. So in our today's class, we will discuss about the game playing strategy, the state of the art resources and the frameworks for that. Specifically, we will discuss about two algorithms, the minimax and alpha beta pruning. So that's the target. Um, then why we need to study the game? There are several types of games. Specifically, we want to win a game. If we think about AI agent, every AI agent will try to beat the opponent. We need to develop the agent in such a way so that it can beat the opponent. Opponent can be another player, another AI agent, or it can be human also. So that's why we need to find out a clear criteria for success. Okay, that means this is the case, clear criteria for success. Whatever the state, whatever the position of the game, AI need to win. Okay, that's why we need to study how can we design an agent. That agent can maybe win a game, whatever the game it is. But development of such AI agent is difficult. Although we have successfully designed some of the AI agents, that is the game agents, and they can easily beat even the expert human being. But still, there are several games. Still, we need to search for or we need to develop intelligent agent which can maybe beat the human intelligence. So another criteria offer an opportunity to study problem involving the hostile, adversarial, and competing agents. In case of our gaming environment, the environment can be hostile, the environment can be adversarial, and it can be competitive. So we need to keep in mind, based on whether the opponent is hostile or not, whether the opponent is adversarial or not, or maybe it's just a competitive agents. Opponent is competitive agent. We have to keep those in mind to design an AI agent for game playing. And also we have historical region. That means there are several games in our history, and those kind of games, if we can design, analyze, and simulate, like the chess is one of the historical game, okay? And it's a fun also. If you can design an intelligent agent, and that can maybe, that's your creation, and that can beat most of the human being, then it's a fun also, okay? And interesting hard problems which require minimal initial structure. Sometimes some of the problems are very difficult, the games are very difficult, but still we need to find out a way that is kind of easier way to design it or restructure it. And sometimes it is difficult also to human being to be an expert on such games. Those kind of games, if we want to design the agent for that, is really difficult also, like the chess. if we can think about a chess game, then you have to think about like 35 to the power 100 nodes in search tree. Okay, and 10 to the power 40 legal states on it. So we will discuss about that is what usually we call the search tree and the legal states also. The typical case, usually we design the agent, AI agent for two-person game. The players alternate moves. That means the first player move, and then that first player need to wait for the movement of another player. That is alternate. That's what the alternate moves. That first player play, then wait, and for the next players playing. And in typical case, the games are zero sum. It means if one player win, then another player will lose. Okay, that is called the zero sum game. And in gaming environment, usually we have the perfect information. That means everyone will know the board. Most of the case, okay, everyone will know the board, the position of opponent players, that is the roles or opponent players' characters. So that is kind of the complete information in front of each and every player of the game. There are several examples for that, like that in tic-tac-toe, in checkers, chess, Go, Neem, Othello. So those are just two-person game and the typical game. But there are some other games also a little bit difficult, like the breeze, solitaire, backgammon. Okay, uh, those are
স্যার মে
difficult
আই
to
ইন্টারাপ্ট?
design. Yes, please.
স্যার এখানে বলেছে নো চান্স, মানে ইউজিং অফ ডাইস ইনভলভ না। তো আমরা যেটা লুডোর গেমিংটা দেখি ওইখানে তো ডাইস ইনভলভ আছে, সো এখানে যে নো চান্স বললো।
So no chance using die. Using dice is just the example.
ওকে স্যার।
Usually like if you have one chance, then no one will offer you another. Okay, that's why it is mentioned no chance.
ওকে স্যার, বুঝতে পারছি, থ্যাংক ইউ।
Then how to play a game? Usually we consider like the gaming environment is like this. They consider all the legal moves you can make. There are several moves or options you can play, but you have to play on the legal moves. And then compute the new position resulting from each move. That means from each and every state, you have to think about what are the new positions, what are the possible new positions I can move from here, and then evaluate each resulting position. That means you have to check each and every alternate positions, and then determine or evaluate your betterment. That means the which positions you want to, you have to move on that position. That is the best position. Okay, that means best position based on the evaluation function. So think about it like we are human being. Maybe we can think about that is which one is the best. But now you have to consider about the AI agent. The agent should think about which one is better for the movement. Okay, so that means you have to design some kind of evaluation function in this case also. The evaluation function. Okay, I think in our genetic algorithm we also have a concept of our um, evaluation function that is called the fitness function. So here is also some kind of evaluation function is necessary. That is which position is the better position you have to think about, and then make that move. That is the best position move, and then you have to wait for opponent to move, and you have to repeat this process maybe until end of the problem. Then what are the key problems in gaming design? What are the key problems? The first problem is representing the board. That means there are several types of games, but you have to think about like how to represent that board. If we consider about the tic-tac-toe, it has a board like maybe the 3x3 grid, and then you can move and then opponent can move like this in those positions. But if you think about a chess board, there is a board, but the the players and the characters are different in that case, not like the tic-tac-toe. Okay, so that's why it's challenging to defining the board for each and every game. So that's why still it's not there. There are several games actually it's not possible, or still uh, we didn't design an AI agent for those kind of games. Generating all legal next boards. That means maybe you are in a state, then we have to think about what are the next possible boards. So you have to think about all the possible movements or all the possible plays. And then the third thing, another problem is evaluating a position. So which position is better? So these are the three key challenges in game design. Okay, that means representing a board, and then you have to generate all the legal moves, and then evaluating a position. There are several evaluation function also, and this evaluation function or the evaluation function for the gaming agent is a little bit different uh, from the evaluation function we have designed so far for the heuristic search algorithms like A star or A. What's the difference? The difference here is the evaluation function in gaming agent. Usually we call it the static evaluator. So it will evaluate the goodness of a game position. What's the difference? The difference here is the contrast with the heuristic search, where evaluation function was a non-negative estimation. So usually we design like in A star search, we consider the heuristic evaluator like the straight line distance we have considered. So all those are just non-negative estimates, like all those are positive values. Okay, from the goal node to our start node, goal node to different nodes, the straight line distance. So those distances, those heuristic values are just the positive values. Okay, but here in this case, the evaluation function, you have to think about your position and the opponent positions also. So that's why sometimes you will get the negative value. So not you will not get always the positive values. Okay? So that's uh, the nature of evaluation function in gaming agent. Okay? So the zero sum assumption allows us to use a single evaluation function for you and the opponents. Okay, that means for both of the AI agents, or maybe one AI agents and the opponents. So usually what we consider the f of n. This is the evaluation function. You can design this evaluation function, and it is solely based on uh, the different games. Different game has different evaluation functions. So f of n, that is the evaluation function or utility function, if it is very greater than the 0, or maybe if it is a large positive number, then the position n is good for me. That means good for me, but bad for you. If we think about you and me, okay, so that means this is the me is the AI agent, and you is the opponent. So on that case, you want to design a AI agent, so that's why me means the AI agent. So f of n is greater than, very, very greater than 0. That means is if it is a positive number, or maybe we can say a large positive number, and then that position is good for the AI agent but bad for the opponent. But if f of n, this f of n, it is less than 0 or very, very less than 0, or we can say less than 0 means it's a negative number, a large negative number. It means the position n is bad for me and good for the opponent. Okay, and f of n is near 0 or maybe 0, it means it's kind of the neutral position. And for the winning case, usually we consider the f of n is positive infinite if uh, AI agent wins. Okay, and if the opponent wins, then usually we call it is negative infinite. Negative infinite. Okay, so this is evaluation function. We have to design the evaluation function, and then based on that, we have to apply some of the algorithms for finding out the best way to move on to win the game. Here, some examples of the evaluation functions are there. Like if we consider about our tic-tac-toe game, okay, the tic-tac-toe game, then evaluation function we can design like the number of 3 lanes open for me minus of number of 3 lanes open for you. So this can be the evaluation function. That is the f of n. Okay? So for each and every state, we can find out uh, the the evaluation score for that board. Like if we consider a board like this, and maybe you can see some of the positions are okay. What's that? Here is a board. That is a tic-tac-toe board, and we want to find out the evaluation function. Evaluation value like uh, this x for me and maybe O for the opponent. Okay, and then maybe uh, this x for me, and uh, then here is the O for the opponent. So we want to find out the evaluation score of this board. So in this case, we can see there is how many ways I can win. I means AI agent can win. So number of 3 positions open for me, as it is mentioned. There is number of 3 lanes open for me. So we need to count that. There is number of 3 lanes open for me. It means I can place, there is X here, and this is the one position I can win. And this column, no, there is no way for me to win within this column. Okay, for using this column, I cannot also win, but this row is open for me, and for this row, this is not open for me, and this row is also not open for me. How about the diagonal? So this diagonal is not open for me, and this diagonal is not also open for me. Okay, so that means both of the diagonals, this diagonal, there is right diagonal and left diagonal, both are not open for me. Okay, so that means you can say how many 3 lanes are open for me. In that case, we can see there is this column and this row only. Okay, so that is the 2. So minus, how about the opponent's case? the opponent's case, it is for the opponent case, we can say opponent can win using this column. It is open for the opponent. Using this column, it is also open for the opponent. And using this row, it is also open for the opponent. And how about the diagonals? Okay, for the diagonals, I think it's not open for the opponent. So 3. Okay, so here is the 3. The evaluation score, like the f of n for this board, it is -1. So -1, it means that actually at this stage, stage, the opponent is in winning direction. Okay, is in winning direction. He is better position than me. Okay. So here example of an evaluation function for the tic-tac-toe. We can apply this evaluation function. The Alan Turing function for the chess, it is this function, that is the f of n equal wn divided by bn, where the wn is the sum of the point value of white pieces and the b of n is the sum of the blacks. Okay, so that means sum of the point value for the white piece and sum of the that is the point value for the black is the b of n, and this is the ratio for that wn by b of n. Okay, so it can be used as the evaluation function for each and every board of chess game. There are several other evaluation functions for the chess, like in Deep Blue. I think most of you know about the Deep Blue. The Deep Blue is one of the AI agent, or we can say the computer, and that computer beats the human in 1997. This is in chess game. Okay, 1997. Deep Blue is developed. The AI agent beat the human Gary Kasparov. And on that case, in Deep Blue, we have designed the f of n, that is the evaluation function. And in that evaluation function, we have considered total 8,000 features. So 8,000 features. And the function is designed like this way. Okay, that is the W1 and the feature 1 of n, W2, that is the W1 is the weight of feature 1 and weight of feature 2, weight of feature n. And then the feature 1, feature 2, feature 3, there are several kinds of features we have considered, like the first feature is the piece count, how many pieces left for me and how many pieces are left for the opponent. And then piece placement, and which kind of, that is the character is placed where, like the placement of king, the placement of queen, placement of the horse in the board's position. Okay, so each and every one we have considered as a feature, and then develop this complex evaluation function for that in case of the Deep Blue. And total 8,000 features are considered. Okay, so that means the evaluation function, sometimes we can say it's easy to design, and sometimes maybe it is difficult to design. Like the chess, this evaluation function is kind of the easy design evaluation function, wn divided by bn. There is sum of the point value of the white pieces divided by sum of the point value of the black pieces. This is easy to design, but for the case of the Deep Blue, we have to design the composite evaluation function. Uh, then the concept of the game tree is like this. That is, we have to think about the state space, the problem space. As I have already mentioned about the state space of our one of the popular game here, the chess. We can say that in our search tree you have 35 to the power 100 nodes. Okay, so now we have to think about what's the search tree or game tree. Like in our tic-tac-toe, we can see there is, this will be the initial board. Okay, initial board that is empty, 3 by 3 go, 3 by 3 board. So initially the board will be like this. So this one, this is the initial state. So this one, we can consider this is the state of the game. This is the initial state, so one of the state. Then the next thing is we have to consider there are several options from here. Like someone can think about the first movement for the X, like the X he or she can place at this position. Okay, so this is another state. Then someone can think about like the placement of the X in another position, like maybe you can say this position. Someone can think about, okay, maybe not this position. We can, the placement of the X can be here. Someone can think about like another position. Maybe this one. Okay, so in this way, several positions we can consider. Several positions we can consider. So can anyone tell me how many possible states from the initial state?
9 states.
Yes, 9 possible states from the initial state. Okay, so that means the 9 possible states. We should consider the 9 possible states. But which one is better for me if we consider that at first I have to move. Okay, at first I have to move. Then on that case, where to move? Okay, so that means we have to evaluate each and every state. Like we have to evaluate this board and then find out the f of n for that. That is f of n for this, f of n for that. And then we have to find out f of n for this board and then f of n for this board. In this way, we have to find out the evaluation function of each and every board. Then the next thing is we have to consider again, like if this one is the first movement, the next movement we can consider from here, the next states. The next states can be from here, the another state like the movement, next movement, okay, maybe for the O. O can be placed in this corner. Okay. The upper left corner, O can be placed. Then someone can think about another state like here. Another states. So X is in center, and we can think about the O is here. Okay, in this position. So this can be another state. In this way, we can consider also several states. Several states. Okay, that means from here we can maybe get several states. So now the next thing is maybe again from any of these states we have to move. Maybe this movement is for the opponent's movement. Then opponent, we can consider that opponent also that is the best player. So opponent will try to find out that is his or her best position. So considering the opponent as an expert opponent, you have to design your plan, or you have to design or develop your gaming agent. And then on that case, maybe after the opponent's movement, you have to think about the next state or next phase. Maybe the opponent movement is this. Then we have to think the next states. Okay, the next states, in those states, X is here, X is there, and then O is here. But now you can move maybe either this position or maybe this position. Okay, so these are also some other states. So there are many other possible states also. So that means if you think about the gaming states and the exploration of those states in hierarchical structure, then you will get a game tree. So this is a game tree. This is a game tree. Okay. So you can say from the initial state, you can get maybe 9 possible states. And then from each and every state, you will get the several states, several other states. And each and every states you have to evaluate, and then maybe you will get what? You will get the evaluation functions values. That means there are several ways of winning the game or maybe losing the game. You have to consider all these cases. And then you have to have some of the value for this. And again, usually we use a static evaluation function. That is, if f is greater than 0, then it is better for me. If f is negative, then it's better for the opponent. In this game tree, the arcs represent the possible legal moves for a player. So that means possible legal moves. That means from the initial state, a player can move to here. So that's why this arc represents a possible legal moves. and another next arc represents to another legal move. So all these are the legal moves, the arcs. If it is my turn to move, then the root is labeled as max node. So if it is my turn to move, then we can consider this one is the max node. Why max node? Because we want to maximize the utility. Maximize the utility. So that's why we can see that this is the max. So if it is my turn, then we have to label it as the max node. And otherwise it is labeled as the min node. That is for the opponent's case. Okay, so at first, this is the my turn. So my turn, if we consider about the my turn, then we have to say that this is the max state. That means I can try to maximize my utility, maximize my profit, maximize my utility. But then after my movement, like my play, so if I play to this direction, so that means at this stage, I have to wait for the opponent's movement. And what opponent will do? Opponent will try to maximize his profit or her profit. That means that will be kind of the minimization of my profit. And this game, or we can say gaming as in design, we have to consider that consider in my aspect. Okay, so that's why this is called the minimization. Okay, so that means it will try to minimize at this stage. It will try to minimize my profit or minimize my utility. Okay, so I will try to maximize, because this at this stage I can move or I can play first. That's why this stage is the maximization step. But this step, we have to consider the minimization step, because the opponent will try to minimize my profit or minimize my utility. So that's why here this is called the min state. So max state, then min state. And after that, maybe after this movement, the opponent movement is this one. So this one. And now this state actually we can say again the max state. Why? Because at this stage, I want to maximize my utility. Again, maybe after this one, maybe I have the play like this way. Okay, so this state is the mean state again. That means the opponent will try to minimize my profit. Okay, so in this way, maybe we can say finally we will get the desired state or goal state or winning state or maybe losing state or maybe kind of the draw state. But each and every stage will provide me an utility value. Okay, utility value or evaluation score. Like you can see, this is the utility value. Here's the positive one. Here's the 0. Maybe this one is the negative one, like this. Okay, these are the utility values. So each level of the tree has a node that are all max or all min. Nodes at level I are of the opposite kind of those at level I plus 1. So that means we can see, if we consider this one is the max, this one we have to consider mean. Again, this one is the max. This one we have to consider mean, like this one. So now here is minimax overview. So in min-max overview, we can say it's a search tree. Why it is search tree? Again, we have to search for the winning path. Okay, winning path. We have to search the winning path. So that's why it's kind of search tree. Okay? So in that case, we can see that a square represents the decision states. So that means this is the state, this is the state, this is another state, and this is another state. And branches are the decisions. That is the move. Okay, maybe I can move from here to here. Okay, so this is move. This is another move like this. Okay, so these are the branches are the moves. And start at root. So that means we have to think about like from here. And nodes at the end are the leaf nodes. Okay, so that means like here we can see there is the utility value we got from here, -1, then 0 and +1. Okay, so these are actually the terminal nodes, or we can say the leaf nodes. And those leaf nodes, if we have the evaluation function, then we will get the evaluation value. So nodes at the end are the leaf nodes. So we can design this game tree also considering the symmetrical positions, removing the symmetrical positions. Okay, removing the symmetrical positions, it means some of the positions are symmetrical, and that's why considering or removing those symmetrical positions will not hamper our total search tree. So that's why we can think about like what are the symmetrical positions of our first move. Like moving in this corner, same as the moving in this corner, same as the moving also in this corner. Okay, so those are the symmetrical positions. So that's why we can consider like all the corners are the same. So that's we can consider same movement. And another movement can be at the center. And what else? The symmetrical movements, we can consider the symmetrical movements if we can move here, or if we can move there, or if we can move here, or if we can move there maybe. So those are also the symmetrical positions. Okay, so that means in the evaluation function, those positions will generate the same kind of values. So those are the symmetrical positions. So that's why from this the first stage, if we consider just three possible legal moves like this one in center, in corner, and maybe in case of the middle positions like here, okay, or maybe there, this position or that position. So those are the symmetrical. So three possible movements. We have removed the symmetrical positions. Okay, so we can consider here is the corner, middle, there is the center and middle. We can design a tree like this way also, removing the symmetrical positions. And these trees are unlike the binary trees. Why? Because in binary trees, every tree has just the maximum number of branches is 2. Okay, so but this is not a binary tree. So it's depend on the game situation. Now we can see from the first move, we can get the 3 branches, but from in the second move, we can see 1, 2, 3, 4, 5, total 5 possible moves. But for the second node, it is just only 2 possible moves. For the third node, it is 4 possible moves. So it is different from the binary tree. And labels usually called play or plays. Okay, so plays, that means we can say the first play, like here is the cross, the first play. Okay, the second play, maybe here is the 0 in center. Okay, so this is the second play. So usually the labels usually call the plays. So this is the first play and then second play like this way. And players call the mean and max. So max is the me and mean is the you. Okay, so that means this stage is the max play and then this stage is the mean play. Okay, so this is called the min max overview. Then what is the minimax procedure? The minimax procedure is a minimax algorithm. So on that case, create a start node as a max node with current board configuration. So you have to think about the start node as the max node. Then expand nodes down to some depth. That is the play, because the levels we can consider those are the play in look ahead game, and apply the evaluation function at each of the leaf nodes. Okay, that means we have to finally evaluate the leaf nodes and we will get some value. Then we have to back up those values. So back up values for each of the non-leaf nodes until value is computed for the root node. Okay, so that means it's kind of the bottom-up approach. Bottom-up approach. That means we have to think about that is the bottom nodes first, their evaluation value, and then the other nodes values we have to calculate based on the minimax procedure. So what's the procedure is at the min node, the backup value is the minimum of the values associated with its children. So that means in min node, it will try to find out the minimum values of the associated uh, child nodes, and at max nodes, the backup value is the maximum of the values associated with the children. Okay, so that is the max values associated with the children. That we have to pick the highest value of the child nodes in max nodes. So that's what I have already mentioned. In max, that means I want to maximize my profit. So maximize my profit. How can we maximize my profit? Maximize my utility, considering that the child please provide me the most the largest value. Okay, uh, but in min node, it's opponent's node. Okay, so it will try to minimize my utility. So what it will do, it will at this stage it will try to find out the node which will produce the minimum value. Okay, so that's side it will try to find out. So pick the operator associated with child node whose backup value determine the value at the root. Okay, so that means finally we have to find out a root uh, from the from the root using the max mean procedure. Okay, this max and mean procedure. So what does it mean? So this is the minimax algorithm's output. Like in this case, if we consider about our game tree, just this is our game tree. If we consider like this one, so these are our static evaluation function, evaluation value, static evaluation value. Like this one is 2, this one is 7, 1, and 8. Then consider that this is the max node and this is the mean node. And these are the leaf nodes. Okay, so these are the leaf nodes, the terminal nodes. So using some form of evaluation function, we got this 7, this 1. And this is 8, like this way. Okay, now we can think about like uh, so here is a 2 and 7. You can see 2 and 7. Then so this is the mean. Okay, this is the mean. So if we can think about like this is the mean. So So this is 2 and this is 7. Between these two child of this mean node, between these two child of this mean node, which one has the minimum value? Like the 2 is the minimum, okay? 2 is the minimum. So that means it will take here 2. So like in this case, that is from this 2, it will take 2 because this is minimization. It will consider the minimum value. Similarly, between these two, which one is the minimum? 1 is the minimum. So it will take the minimum here, 1. And now we can think about this one. This is the maximization phase. So it will try to maximize the utility. So between these two values, which one is the maximum? The maximum is 2. So it will consider here 2. Okay. So that means this is the node. So in this case, now we have to determine the search path, or we can say winning path. So we can see this 2 is from here. Okay. So this 2 is from here. So it will move in this direction. So it will play, it will move in this direction. Okay. It will play in this direction. Now from here, where to move? Then this 2 is from also from here. So that is from here, it will move in this direction. Okay. So this is the path. This is the winning path for the agent, winning path for the agent. So this is how the Minimax algorithm actually try to find out the winning path. Like now a little bit larger tree, or you can say the depth of the tree here is 3. And on that case, if we consider about this is the max, and then mean, and then again max, and then these are the terminal nodes. Okay, these are the terminal. And for the terminal nodes, we have computed their evaluation score. The evaluation score for this one is 4, this one is -5, this one is -5, and this one is 1, this one is -7, 2, -3, and -8. Now, so here's the max stage, then mean stage, and then max stage again. So what it will do, we can consider that this is the max stage. Okay, so if we consider the terminal nodes or child node of this D, the child node of this D, you can see the child is the 4 and 5. But here is the max stage. That means it will try to find out the maximum one. So which one is maximum? 4 and -5. 4 is the maximum one. Okay, 4 is the maximum one, and therefore it returns 4 here. Okay, it returns 4 here. Similarly, for this E node, it will try to find out the maximum. So -5 and -1, then -5 and 1. So 1 is the maximum. So it will pick the 1. And then here's the -7 and 2. Which one is the maximum? The maximum is the 2. So 2 is here. And between -3 and -8, which one is maximum? Maximum is -3. So -3 is here. And now in mean, so this is the mean node, and the child of this node is this 2, this one and that one. So these 2. So here's the minimization phase. It means it will try to find out the minimum value. So 4 and 1, the minimum is 1. So that means this is the 1. So here is 1. The value is 1. Now here is 2 and -3. Which one is the minimization stage? The minimum is -3. Okay, -3. So here's the -3. And now we have to consider about our root. So in this root, we can see that this is the max stage. So max stage, it will try to find out the maximum value, or it will try to maximize its utility. So here is the 1. We can see this is the child nodes of this node is just 2. So between these two child, the value for this B is 1 and C is -3. Which one is maximum? The maximum one is 1. Okay, maximum one is 1. So it will take just 1. Okay. So now we want to determine the search path to find out the optimal value or optimal utility. So we can see this one, actually this one is taken from where? Taken from this node. So that means it will play this one. Then from here, this one is taken from where? This one is taken from this node. So that means this is the path for that. And then this one is taken from this node. Okay. So that means the next play is this. So this will be the search path. Okay. This will be the search path for that. Okay. So this is the minimax procedure to find out the search path. But actually the algorithm works using the depth first procedure. Okay, depth first procedure. So that's why if we can apply the minimax procedure in this tree, then I think it will be better to understand it. So what does it mean? It means that we can see here that the max node. Okay, so this is the max and this is the mean, and these are the terminal nodes. And the evaluation function, that is the f value for the terminal nodes, are this is 3, 12, 8, and 2, 4, 6, like this. Okay. Now we want to apply the minimax algorithm. So what it will do, as I already mentioned, that it follows the depth first procedure. So it will try to explore like the depth. So that means it will move from here to there, and then it will move to this position. And we can see it finds the 3. Okay. So this 3, it will this 3, this is the evaluation value. So here's the minimization. That means it will try to find out the minimum value. So at first it will consider that this 3 is the minimum one. Okay, minimum one. Now it will explore another branch, and here is the 12. So it will compare the 12 with the 3, the which one is minimum. The 3 is the minimum. Okay, so it will keep the 3. Now it will explore another node, that is 8. And then 8, it will compare with the 3, this 3. And again, the which one is minimum? Minimum is 3. So it will keep this 3 here. Okay. So that means from this branch, it will find out the minimum, that is the minimum is 3. Now, what it will do, according to our depth first principle, it will move here, okay, and try to find out the another branch, okay, another branch. But when it is moving here, on that case, we can see from this branch, it will get a value that is 3. So that's why it will return here 3 first, okay? And then it will try to explore the second node. So it will move into the depth. In the depth, it will get what? It will get 2. So here is the 2. Okay, here is the 2. And then it will explore another branch. Here is the 4. And 4 and 2, it will and we need to find out. It will try to find out that is 4, 4, and 2. Which one is minimum? Minimum is 2. Again, it will try to explore another branch, that is the 6. Between 6 and 2, which one is minimum? 2 is the minimum. So here is the 2. it will keep the 2 here. And then now we can see this is the maximum stage. So here's the in this max, here is the 3, and in this branch this is the 2. So which one is maximum, 3 or 2? Which one is maximum? Maximum is 3. Okay, so it will keep the 3 here, and then it will again explore another branch. Okay, another branch here. Then go to the depth. Then here is the 14. At first it will move 14 in this position, and then it will explore another branch. This branch, the value of this branch is 5. Between 5 and 14, which one is minimum? Minimum is 5. So instead of 14, it will replace here is 5 as the minimum one. And then it will explore another branch, and in this branch it will get 2. Then it will compare 2 with the 5. Which one is minimum? Minimum is 2. So instead of 5, it will get the 2 here. And now we can see this 2, it will move back to here. And then we can see this is the max stage. And maximum already here is 3. And it will compare with these 2. Which one is maximum? It is between 3 and 2. Which one is maximum? 3 is the maximum. So we can see it will return the 3 here. Okay, return the 3 here. That means from this minimax algorithm, it will get the 3 in root node. But how the 3 it has been taken? How the 3 has been taken? The 3 actually is from which branch? 3 is from this branch. Okay, so that means it will try to find out the source path now. So this is the path, and then from where it will get the 3. That means we can say this 3 is here. So that means this is the path. This is the path. Okay, so the algorithmic principle, it will follow the depth first principle, okay, to find out the minimax. So minimax algorithm that is a complete depth first exploration, okay, depth first exploration. So if we consider the depth M with B legal moves, okay, if we consider about the B legal moves, then the time complexity, if we define the time complexity, it will be order of B to the power M. It's same as our depth first search, order of B to the power M, where M is the depth and B is the legal moves or branch. And space complexity is the same as our depth first search also. It is order of Bm. Okay, here is the Bm, order of B times M. In case of the chess game, the M, this M, nearly 35. And on an average, the B, that is the branching factor or legal moves, is between 50 to 100 within this. Okay, so that means considering the time complexity, it will be the B, like we can say, if we consider B is 100, the 100 to the power M is 35. Or we can say minimum, it can be 50 to the power 35. Okay. So, so that means we can see that is the source space is huge on that case. So that's why most of the games, if we can think about like the early the computation, so it is kind of impossible to consider all those states before moving just one play. Okay, it is impossible. But nowadays, the powerful computers are available, so that's why designing such kind of games are also a little bit easier. This is another game. There is a name game tree. So here is the problem is given. You can try to find out the solution for this. Try to find out the develop the game tree. Okay, so the statements is given here. It's a kind of the problem is given. You can try. Now, how to improve our minimax algorithm? The minimax algorithm, how to improve that? For the improvement, one procedure is called the alpha beta pruning. I think you know the pruning. Pruning means a part of the tree we have to cut off. We will not explore that part. Okay, so that's called prune or pruning. And alpha beta is the procedure for that. Okay, so we can improve the efficiency of our minimax algorithm using the alpha beta pruning. So the alpha beta pruning is an extension of our minimax algorithm. So the basic idea for that is if you have an idea that is surely bad, don't take the time to see how truly awful it is. Okay, so that means uh, if we already know that uh, that is we will not get the better value for from this branch, then no need to explore that branch. Just cut off this branch. So that's the philosophy here. Like in this case, the very small tree, we can say this is the max stage and this is the min stage. If we consider that these are our terminal states, okay, terminal states, and then we have some evaluation value like 2, 7, 1, and this is unknown. Maybe we didn't explore it yet. Then we can see that is according to the minimax algorithm. Here's the mean. Okay, so that means between these two values, which one is the minimum? Minimum is 2, so we can get the 2 here. Okay, we can get the 2 here. And even though we didn't explore this part yet, so we can see there is 1, and whatever the value it is, if we consider that is currently we just explore this 1, and then the minimum value is 1. Okay, minimum value here is 1. And then between these two, which one is maximum? 2 and 1, which one is maximum? Maximum is 2. Maximum is 2. Okay. Even though we didn't explore this part, but still we can say that the max in that node, the evaluation function will be greater than or equal to. Why? Why we can say this without exploring this part? Because we can see that is from this branch, we already got 2. Okay, we already got 2. And then if we explore this branch and at the first site we got the 1, this one. Okay, this one is less than the 2, that is 1 is less than 2. This is the 1. We can say this is the mean stage. There is the minimum phase, minimum stage. So in that minimum stage, so we got 1. So at least in that value, this value we can get the 1. Or maybe if we consider that this one is maybe 5. And between 5 and 1, which one is minimum? 1 is minimum. So we will get the 1 here. If we consider this one is, there is 100. Again, we can see between 1 and 100, which one is minimum? Minimum is 1. So 1 will be there. And if we consider about our the negative value, maybe we can say the negative 5. Between 1 and -5, what we will get here? We will get the -5. Okay, -5. If we get the -5 or maybe -100 even, already you can see this stage is max stage, and we got the maximum value 2. So between 2 and whatever the negative values we get, between 2 and whatever the negative values, like -5 and -100, which one is the maximum? Maximum is 2. Maximum is 2. So that means we will get the 2 here. So it means no need to explore this part. No need to explore this part. That is, without exploring this, we can see that we can determine the max value here. So that's why we need to prune it. That means we need to just cut off this part of the tree exploration. So that's the principle of our alpha beta pruning, but it has the algorithm. So we will see the algorithm. Again, the alpha beta pruning, it is also it will follow the same procedure like the minimax. That is the depth first order. Okay. At each max node n, the alpha beta. So two things here, alpha and beta. Alpha of n, it means maximum value found so far. So alpha in max node, it means that maximum value found so far. Alpha is maximum value found so far. And beta in min node, it means minimum value found so far. Okay, so that means alpha, it will hold the maximum value found so far, and beta will hold the minimum value found so far. And then we will have two cutoff, like beta cutoff and alpha cutoff. The beta cutoff and alpha cutoff. So alpha cutoff, it will be in the min node, and beta cutoff, it will be in the max node. Okay, so when it will cut off, the cutoff, if the alpha cutoff, if beta of n greater than or equal alpha of I, then we will the cut of the alpha branch. And then the alpha, the beta cutoff, when we can perform the beta cutoff, if the alpha of n is greater than beta of I. Okay, so on that case, we will perform the beta cutoff. We will see with the example also. So let's say this is the search tree, and is given like these are the terminal nodes. Okay, these are the terminal nodes, and the evaluation function values are these 3, 12, 8, 2, 12, -2, 14, 1, and -1. And then in alpha beta pruning, what we have to do, we have to initialize. That means we can see this is the max and this is the min node. Okay, max and min. So in max node and min node, we have to evaluate the alpha beta for each and every branch, and the value for each and every that is node other than the leaf nodes. So we can see here, this is the max node. We have introduced a variable that is the value, v, and in min node we have introduced the value v. Okay, these are the v. And for each and every branch, we can see we have the alpha and beta. Okay, alpha and beta. Now we have to initialize the max node, the v of the max node, infinite, with negative infinite. Okay, with negative infinite. So v is negative infinite for the max node. Why? I think most of you already know that, specifically in case of our programming, like from a list of values or the array of values, we want to find out the which one is maximum. So usually if we consider or define any variable like the v, and initially we assign the v like very large negative numbers and consider that that is our maximum. Okay, following the same principle, the maximum, in case of the maximum, we can think about like the v is negative infinite. That means a very large negative number is the v. Okay, because we want to find out the maximum. And for the case of the minimum, this is the mean. On that case, we can see there is positive infinite, and positive infinite. So here the v, p, and v. In that case, we can see these are the positive infinites. Okay, we want to find out the minimum value. That's why initially we can say very large number is the minimum one. Okay, so here v is negative and v is positive. Okay, for the max, the value v is negative. For the mean, the value the v is the positive infinite. And now the alpha and beta, we can see for this branch, the alpha and beta. So alpha and beta, and again, first alpha. Alpha, as I already mentioned, the maximum value found so far. The maximum value found so far. The maximum value found so far here is maximum. That's why we have assigned the negative infinite. And beta, we have assigned the minimum value found so far, and the minimum value is positive infinite. Okay? Positive infinite. This is the initialization of the board. So we will apply the alpha cutoff and beta cutoff. We can see, you can test this condition, that is alpha of n greater than or equal beta of I for the beta cutoff at max node, and alpha cutoff in min node, the beta of n greater less than or equal alpha. Okay, so then we will apply, or we can consider our testing this one, that is instead of beta you can consider testing v value with the beta and alpha, like here. For the beta cutoff in max node, v of n is greater than, instead of alpha of n, we can test the v of n greater than equal beta of I. And for the alpha cutoff, it is v of n less than alpha of I. Okay. So now we can apply the algorithm. So what we will do, we can see this is this value, this is alpha value. We have to pass to downwards, following the depth first principle. Okay, so that is alpha negative infinite and beta positive infinite. We can see here alpha, so this value we have to pass here. So that means we will get alpha negative infinite, beta positive infinite. So here alpha negative infinite, beta positive infinite. And then following the depth first principle in the same as the minimax algorithm, what we will get 3. Okay, at first we will get the 3. Then 3, this 3 will update it here. Okay, so updated here. This is the mean node. So this is the mean node. So mean node, that means the value of the mean node will be updated following the principle, this one, that is the v will be the mean of the existing v and this 3. Okay, which one is the minimum one between these two? So v will be the existing v. Existing v is what? Existing v is positive infinite. So positive infinite and 3. Between these two, which one is the minimum one? Minimum is 3. So here is the 3. Okay, so here is the 3. So that is the v will be 3. So that means this one is 3, then the value will be updated. Value will be updated to 3. Okay. Using this principle, that is the which one is minimum. This 3, because here is the minimum. Okay, minimum. So this 3 and the value, which one is minimum? The minimum is 3. Okay. After finding out this value, we have tried to prune it. Okay, following this min node. So in the min node, we will try to use the alpha cutoff. Okay, alpha cutoff. That means we have to consider this equation. whether v of n, this v of n, that is the 3, this is the 3 is less than alpha of I. So alpha of I is what? It is negative infinite. Negative infinite. So whether this 3 is less than or equal negative infinite or not, actually this is not true. Okay. If not true, then no pruning. So we cannot prune at this stage. So that's what I have written here. As v less than alpha, so you can say this is the alpha cutoff. We want to apply the alpha cutoff here. That is the 3 less than equal negative. This is not true. So that means no pruning. We cannot apply pruning at this stage. So if no pruning, on that case, we have to update. We have to update the value of beta. So we have to update the value of beta using this equation. This is the minimum of existing beta value and the v value. So existing beta is what? Positive infinite, and v is what? V is 3. So between these two, which one is minimum? The minimum is 3. Okay, so minimum is 3. So beta will be updated. So beta, now beta is 3. Then alpha is negative infinite. So at this case, just only beta will be updated. Okay, beta will be updated. So in this case, we can see this is a minimization stage. So minimization stage, so, the beta will be updated on that case. In maximization stage, alpha will be updated on that case. Okay, so minimization stage, the beta will be updated. So updated beta is alpha negative infinite and beta is 3. Now this alpha and beta, these values, it will pass to our next branch. So next branch is alpha and beta. So the alpha will be negative infinite and beta will be just 3. Okay, so you can see here, alpha is negative infinite, beta is 3. Now again, we will explore the next node. So next node, that is the 12, we will get the 12. So now we will try to update the v again. Previously we have the 3, v is 3, but now 12. Between these two, which one is minimum? You can see here, v and 12. The v is 3 and 12, new value is 12. Which one is minimum? Minimum is 3. So that means the previous one, it holds the previous values. Okay, that is the 3. Now what we have to do, again we have to try, that is in mean phase. In mean phase, we have to try the alpha cutoff. So alpha cutoff, that means the v is less than alpha or not. So we have to check it for pruning. V is less than alpha or not. V is what? V is 3 and alpha is negative 3, negative infinite. So you can see it's not true. So that means at this stage, we cannot even prune. So when we fail to prune, then what we have to do, we have to update the beta again. So update the beta according to the same equation, minimization of beta and the current value of v. So that is this using this equation, minimum beta and v. So you can see at this case, the beta is 3 and v is also 3. Which one is minimum? Which one is minimum? Minimum is 3. So beta is 3. So after updating the beta, we have to pass this alpha and beta value to next branch. So next branch is alpha is negative infinite and beta is 3. So here's alpha is negative infinite, beta is 3. Then we will get the new value of our, that is this node. So 8. Now after getting this 8, the v will be updated using this equation. The previous value of v and the current value of this node. Which one is minimum? So you can see previous value of v is 3 and new value of this node is 8. The minimum is 3. Okay, minimum is 3. So v is 3. The previous value, it will hold the previous value. Okay, after updating this one, it will try to again prune, but we can see there is alpha is 3 and beta is so v is 3 and alpha is negative infinite. So this is also not true. So that means at this stage we cannot prune. Okay, we cannot prune. And for that, in that case, it will update the value of b, and we can see b will be minimum of beta and v, and v is 3. Previously, beta is 3, so minimum. So that means no chance of alpha and beta values. So then it will try to find out another branch, but we can see that there is no other branch here, and no other branch at this stage. So from this branch, it will get what? It will get just 3. It will get just 3. So now that means this 3, it will be considered in this node because this is the first branch. So using the depth first principle, so this 3 will be uh, sent to the max node. Okay, so this is the max node. So in the max node, that means we got the 3. We got the 3. So in max node, this b will be updated now. This b will be updated according to the equation. But this time you can see in this node, we will try to find out the maximum. Okay, maximum. So this is the equation for the v equal be max of p and 3. Okay, so this 3 from this node, and the v is existing v. So existing v is negative infinite. Between the negative infinite and this 3, which one is the maximum? Maximum is 3. So that's why the v is max here, 3. Okay. Now, after v, what we have to do? We have to apply the pruning. Try to apply the pruning, but this time we have to apply the beta pruning. Okay, because in max node, in max n, we have to apply the beta pruning. So beta pruning, that means there is v of n greater than or equal beta or not. So v of n is 3. So here is the v of n is the 3, and the beta of I. This time the beta, we can see this is the beta. Beta is what? Beta is positive infinite. Okay, beta is positive infinite. So whether this condition is true or not. So it is not true. Okay, 3 is not greater than infinite. Okay, so that means no pruning. We cannot prune at this stage. So if no pruning, then what we have to do? We have to update the alpha at this stage. Alpha. Okay, because this is max node, the alpha will be updated. So we will try to update the alpha. Alpha max of, here's the existing alpha and v. So existing alpha is what? Existing alpha is negative infinite and v is 3. Between these two, which one is maximum? Maximum is 3. So we can see now our alpha will be 3. Okay, so here is the alpha is 3 and beta is positive infinite. Positive infinite. One thing you have to notice that previously we have at this branch, this is alpha is negative infinite and beta is 3. In depth first principle, only the value of v is sent to our max node, but not the alpha beta values. Okay, so alpha and beta values we cannot we cannot shift or we cannot move in upward direction. We cannot move the alpha beta values in upward direction. So alpha beta only we can move in the same level. Okay, same level of same branch, and also we can send the alpha beta value downwards. Okay, so like when we start our simulation here, this alpha beta, we send it to the downwards. We send this alpha beta to this branch, and this alpha beta to this branch. Okay, so that means alpha beta can be sent to downwards, or within the same branch we can move just from one branch to another branch, but we cannot move the alpha beta to upward direction. Okay, so now the alpha beta is updated. Okay, updated. Now this value, you can see this is alpha beta. So now we can see this alpha beta, we can send it here in this branch, because these are the same branch. Okay, so here's the alpha is 3 and um, beta is positive infinite. Okay, positive infinite. Now this value we have to send downwards. Okay, downwards, like at first here alpha is 3, beta is positive infinite. Yes, alpha is 3, positive infinite. Now we have to explore the first node. This is the first node. First node is 3. Sorry, first node is 2. So this 2 here, the V is updated on that case. The V will be updated. Now this is the min node. This node is also the min node. So that is the minimum between the previous V and the 2. So here the between the previous V and 2, which one is the minimum? Minimum is 2. Okay, so here the V is 2. Now after updating the V, we have to check for the cutoff. Okay, that means this is the min node. So on that min node, we have to apply the alpha cutoff. We have to apply the alpha cutoff. Then for the alpha cutoff, we can see we have to check whether V of n, there is the 2, and alpha of I. So alpha is what? Alpha is 3. So we can see whether 2 is less than equal 3 or not. Yes, this is true. Okay, that means 2 is less than 3. So 2 is less than 3, the alpha. Okay, so what we can do, we can prune it. Okay, this is true. It means the prune it. The prune it means no need to explore the other branches of this tree. Okay, so you can say, so these are the sub branch. So we have to cut off this. No need to consider others. And why no need to consider? Because you can see already we got the 3 in max stage. And from here, we got the minimum, that is the 2. Whatever the other values we got here, actually, the 3 will not be replaced. Okay, 3 will not be replaced by this 2. That's why no need to explore the other nodes of this branch, okay, of this branch. So it means from here, what we got, we got just 2. And now we have to update the V, okay, the max, using the max equation. So max is our V and 2, which one is the maximum between 3 and 2? Maximum is 3. So here is the 3. There is the 3. Now we have to again try to apply the cutoff. For the cutoff, this is the max. So in max, we have to apply the beta cutoff. That means we have to check whether V is greater than beta or not. So now we can see that is here is the 3. This is our V. V is 3. So V is 3 here. And the beta is positive infinite. Okay, the beta is positive infinite. Positive infinite. So 3 greater than equal to positive. Is it true? No, not true. So if it is not true, then we have to update the alpha. Have to update the alpha using the max equation. So here is the max equation. Max is maximum of there is the previous alpha and V. So you can see there is the V is 3 and previous alpha is also 3. So maximum is 3. Okay, so this alpha is 3, beta is infinite. So we have to pass it to the next branch of same depth. Okay, so here is that means alpha is 3 and beta is positive infinite. Here is alpha is 3, beta is positive infinite. And then what we have to do, we have to pass this one downwards here. So alpha is 3, beta is positive infinite, positive infinite. Now explore the node. This is 14. Okay, here's the 14. So if we get the 14 here, then it will update the value of V. And you can see this is the mean stage. So according to the, minimization objective or minimization formula. So here is the minimization of existing V and this 14. Existing V is what? Existing V is positive infinite and 14. Which one is minimum? Minimum is 14. So here is the 14. Okay, after updating the V, we have to apply, we have to try to apply the pruning. And this time for the mean stage, we have to apply the alpha cutoff. Okay, and for the alpha cutoff, this is the alpha cutoff, that is V of n. V of n is what? 14. Whether this one is less than or equal alpha or not. So alpha is what? Alpha is 3. So 14 is less than 3. Is it true? No, not true. So that means no pruning. You cannot prune. Okay. So that means if it is not possible to prune, then we have to try to update the beta. Okay, the beta. Again, using the minimization principle. So here the minimum existing beta and new V. So existing beta is infinite, new V is 14. So that means beta will be 14 in that case. Okay, alpha is 3 and beta is 14. So we have to pass this value to the next branch here. Alpha 14, alpha 3, beta 14. Now we have to explore this node and it is 1. And now after getting this, we have to update the V using the minimization principle. There is minimum of existing V and new explored values 1. So here is minimization of existing V, it is 14 and new value 1. Which one is minimum? Minimum is 1. So here is the 1. Okay, here's the 1. And after that, we have to apply, again, try to apply the, that is cutoff. Which cutoff? Here is the minimum minimization node. We have to apply the alpha cutoff. Alpha cutoff, that means V of n. So V of, try to apply the alpha cutoff. So V of n is 1. Whether this one is less than alpha or not. So alpha is 3. So 1 less than equal 3, this is true. Okay. So that means, okay, we can apply the prune. So that means here, this is the pruning. Okay. So we no need to explore or expand this node, okay. So from here, what we get the V equal 1, V equal 1. Now we have to update our there is the V of max node using the maximization principle. Okay, so previous V and new 1. Which one is maximum? So previous V is 3 and new 1 is, here is the 1. The maximum is 3. Okay, so here is the 3. Then we can see that is after that we have that is the finished the searching, and finally we got the 3 here. Okay, in our root node, the 3. And then this 3 actually is from which V? This is the V for that. This is V is 3. Okay, so we have to move this direction. And then this 3 is from which node? We can say this 3 is from this node. That means, so this will be the search path for that. Okay, and that's the alpha beta pruning. So that means in alpha beta pruning, this is an upgradation of the minimax algorithm, where we can see that is without exploring a part of the tree, we can get the optimal result. Okay, and this is the algorithm for that. As very easy algorithm. This is the max value This is the mean value. We can see the alpha is the best max so far, beta is the best mean so far. If terminal test, that is if this one is terminal, then return the utility value. And then this is the max value. In that max value, the v is mean, we have initialized with negative infinite, as we have already done. But this is the mean value. For this mean value, we can say v is the infinite or positive infinite. Okay. And for each s in the successor of the state, that is for is x, the v will be updated according to here in max value. Using the max value, this is the value, and then mean value of this stage. So we can see this is the mean value. That means to calculate the max, we have to calculate the mean. Like here, to calculate the max, this max, we have to calculate the mean first. Okay, like here, mean value. Then this is the mean value stage. Then for the mean value stage, if this one is the utility or terminal node, terminal test, like here, these are the terminals. Okay, these are the terminals. Then 3 will be returned. Okay, so here, on that case, the 3, then return utility state. So utility state, the 3 will be returned here. Then max and v and the 3, which one is the maximum? The v is the maximum. And then try to apply the cutoff here. Okay, if v is greater than the beta cutoff, then return the v. Okay, and otherwise we can say alpha, we have to update the value of alpha using this equation. Which one is the maximum? Alpha and v. Okay, the similar equation is here also. So this is kind of the assignment. You can apply the alpha beta pruning. No need to submit the assignment, just try to solve it. Okay, there are several other algorithms also. So what's the effectiveness of alpha beta? And we can see that is alpha beta is very effective. Specifically, you can see that in deep blue design, that is in chess game design, they found empirically that alpha beta pruning means the average branching factor at each node was about 6 instead of 35. Okay, so that is a huge difference. Okay, huge difference. So if the tree is huge, specifically the game tree, if we consider the game tree, you need to design the huge tree for that case. But the alpha beta pruning, actually, it will reduce your search space and the complexity of searching also. So in worst case, we can say no pruning case, it will be the same on that case, that is alpha beta pruning, and minimax will return the same. But for the best case, we can say it will be 2b divided by d by 2 leaf nodes. Okay, the result you can search the twice as deep in min max, like the you will get the at least the half of your complexity. So that's why the alpha beta is effective. Okay, I think that's all in our today's lecture. If you have any question, queries, then you can ask.
স্যার আলফা বিটা প্রুনিং এর কোশ্চেন কেমন হবে, কি টাইপের হবে একটু বলে দিতে ভালো হয়।
এখানে কোন একটা গেম সেটিং থাকবে, গেম সেটিং ইউজুয়ালি যেটা হচ্ছে সিমুলেশন টাইপের কোশ্চেন। আমি আগেও বলছি, এখনো বলি, কোশ্চেন হচ্ছে দুটা টাইপের হয়ে থাকে। একটা হচ্ছে সিমুলেশন বেসড আর একটা হচ্ছে থিওরি বেসড। সাধারণত 10 মার্কসের কোশ্চেনে আমরা 3 মার্কসের থিওরি দিই আর 7 মার্কসের হয়তো বা সিমুলেশন। 3 মার্কসের থিওরি যে কোনোখান থেকেই হতে পারে, এখানে আলফা বিটা প্রুনিং এর অথবা মিন ম্যাক্সের অথবা বেসিক গেম ডিজাইনের উপর যে কোনোখান থেকেই কোশ্চেন হতে পারে। আর সিমুলেশন কোশ্চেনটা সাধারণত কোন একটা গেম দেয়া থাকে আর কি। ইভালুয়েশন ফাংশন হয়তো তোমাকে বের করতে হবে। ইভালুয়েশন ফাংশন বের করার পর সেই ইভালুয়েশন ভ্যালু গুলা এরপর হয়তো বলা হবে যে ঠিক আছে, এখানে তুমি মিন ম্যাক্স অ্যাপ্লাই করো অথবা তোমার আলফা বিটা প্রুনিং অ্যাপ্লাই করো। যেমন একটা গেম আমি এই যে বললাম যে এটা একটা গেম সেটিং, এখান থেকে তুমি গেম ট্রিটা ড্র করবা। তো এখন গেম ট্রিটা ড্র করবে, এরপর হচ্ছে তোমাকে ইভালুয়েশন ফাংশন যেটা, একটা ইভালুয়েশন ফাংশন দিয়ে দেওয়া হতে পারে অথবা বলা হতে পারে যে তুমি একটা ইভালুয়েশন ফাংশনও ডিজাইন করো এখানে। তারপর হচ্ছে আ একটা ট্রি হয়তো দেয়া থাকবে। সেই ট্রিটাতে তুমি আলফা, বিটা প্রুনিং এপ্লাই করে তোমার হচ্ছে কোন পার্টটাকে প্রুন হবে, কোনটা হবে না। তারপর সার্চ ফাইনালি হচ্ছে উইনিং প্যাথ যেটা সেটা কোনটা এটাকে ফাইন্ড আউট করতে বলো।
জি স্যার, বুঝতে পারছি। থ্যাংক ইউ।
ওকে, থ্যাংক ইউ।
স্যার মঙ্গলবার কি ল্যাব হবে?
আ কেন? টিউসডেতে মানে ল্যাব হবে না কেন?
স্যার বুধবারে ৩টা এক্সাম ছিল স্যার, এই জন্য একটু সমস্যা ছিল আমার।
আচ্ছা। আ এটা তোমাদের তাহলে ডিসিশন। তোমরা যদি না করতে চাও সেক্ষেত্রে আল্টিমেটলি তোমাদেরকে